Introduction to Discrete Probability Distributions. In this section, we will discuss the two types of random variables: discrete probability distributions, the expected value of a discrete random variable, and the variance and standard deviation of a discrete random variable. A random variable is a numerical description of the outcome of an experiment. If we roll a die, we could get a 1, 2, 3, 4, 5, or 6 on the face of the die. Therefore, we can call the value that we get on the face when we roll a die a random variable. A discrete random variable may assume either a finite number of values or an infinite sequence of values. A continuous random variable may assume any numerical value in an interval or collection of intervals. Some examples. We can allow x to represent a discrete random variable, where x is the number of raffle tickets sold in one day where the seller has 20 tickets to sell. Clearly, our x value could equal 0, 1, 2, 3, 4, all the way up to 20. For this example, some of us may have been tempted to say that the number of raffle tickets sold in a day was a continuous random variable because the person could sell anywhere between 0 and 20 tickets in a day. This is inaccurate because a person could not sell 4.2938742 tickets in a day. In fact, a person could only sell whole numbers between 0 and 20 tickets. You can only declare something a continuous random variable when all values in an interval are possible to occur with no exceptions. For this example, there are exactly 21 different values that could occur in terms of the number of tickets that could be sold, numbered 0 through 20. Therefore, there are a finite number of options that this random variable can take on, fitting the definition of a discrete random variable. With another example, let x represent a random variable in which it's the number of customers that enter a McDonald's restaurant in one day. For this example, x can take on 0, 1, 2, 3, 4, 5. In actuality, any positive whole number. Since this random variable can take on an infinite sequence of values, we can declare that this is a discrete random variable. Now, an example for a continuous random variable. Let x represent the time that it takes the server at McDonald's to fill your order. In my experiences, x could equal any value between 0 and 5. This is a continuous random variable because x could take on any value in this interval with no exceptions. If we had a stopwatch with exact precision, it is possible that it could take 2.4978924 minutes for a server to serve or complete my order. Therefore, this random variable is indeed a continuous random variable. Let's go through a few more examples to make sure that we could differentiate between discrete versus continuous random variables. For the first example, the number of multiple choice questions you get correct on a 20-question quiz. Would this random variable be considered a discrete or a continuous random variable? If you answered discrete, you're correct. A person could get 0, 1, 2, 3, 4, 5, up through 20 questions correct on a multiple choice quiz. For the second example, the time that it takes to complete a 5-question survey. Is this a discrete or continuous random variable? This is a continuous random variable. If a person was allotted up to 30 minutes to take the survey, it could take the person between 0 and 30 minutes to complete the survey. Since it is possible that any value in this interval could occur, this is a continuous random variable. The next example, an auditor reviews a stack of returns, the number of tax returns that contain errors. This would be considered a discrete random variable. If there were 50 tax returns in the pile, it is possible for 0 up to 50 of the tax returns to contain errors. Since it is not possible for 7.924 tax returns to contain errors because only whole values in the interval from 0 to 50 could occur, this would be considered a discrete random variable. The age of your college professor. Would this be considered a discrete or continuous random variable? In my experience, I have had professors ranging from 26 to 88 years old. This would be considered a continuous random variable. If we were to get down to each second, a professor could be any age between 26 and 88 years old. Since any value in this interval with no exceptions could occur, this would be considered a continuous random variable. The probability distribution for a discrete random variable provides the associated probabilities that the random variable will take on each possible value that it may assume. In layman's terms, a probability distribution gives you all of the values that the random variable can take on and the probability of it taking on each of those values. We can describe a discrete probability distribution with a table, a graph, or an equation. The discrete probability distribution is defined by a probability function p of x. In general, probability functions are defined by a probability function f of x. For discrete probability functions, p of x is the same as f of x. The function p of x gives the probability that the random variable takes on the value x. Here, we have a tabular display of a probability distribution. A telemarketing company called 40 potential customers and recorded the frequencies of the number of magazines purchased by each customer. Since this company sells 4 magazines, this table provides a probability distribution. In the first column, it gives you all of the values that the random variable can take on. And in the second column, it gives you the probability of taking on each of those values. Here we have a graphical display of a probability distribution. Along the x-axis, it gives the number of magazines that could be purchased or the different values that this random variable can take on. The height of each of the bars provide the probability of taking on each of those values. Here we have an example with a probability distribution function displayed as a formula. A casino has a slot machine that costs $1 to play. The machine is set up so that a person could lose $1 if they play, win $0, which means they put $1 in the machine and get $1 back, or gain $1, $2, or $3. The following equation describes the probabilities associated with potential winnings. We're given all of the values that this random variable can take on, and a formula that we can use to compute the probability of it taking on each value. If we plug each possible value of x into this equation, it will provide the probability of assuming that value. All discrete probability functions must follow these two major rules. The first, all probabilities must be greater than or equal to 0. The second, if you sum the probabilities of all potential discrete random variable values occurring, they must sum up to 1. Let's revisit example 1. We should first note that all of these probability values are greater than or equal to 0. Next, if you sum all of the probability values, you will see that they sum to 1. Therefore, example 1 is a valid probability distribution function. How about example 2? Recall, we were given this p of x function for example 2 and the corresponding values of x that can occur. If we plug -1 into this equation, we will obtain 5/15. If we plug 0 into this equation, we will obtain 4/15. If we plug 1 into this equation, we will obtain 3/15. And following the same process, we'll find that the probability that x equals 2 is equal to 2/15, and the probability that x equals 3 is equal to 1/15. The expected value of a discrete random variable. The expected value of a discrete random variable is the same as the population mean. The mean of a discrete random variable is denoted mu sub x. Recall from chapter 3, if we had all of the values in our population listed, we could compute the population mean by summing up all of these values and dividing by the total number of items in the population. However, with a discrete random variable, you are not given all of the values in the population. Instead, you are given how the values are distributed throughout the population via a probability distribution function. The expected value of a random variable x is denoted E of x. The expected value gives the long-run average value of the random variable. For example, in example 2, we were given all of the values that could occur in the population and the associated probabilities of these values occurring. If we were to sit back and watch thousands of people play the slot machine in this example and recorded their exact winnings, the expected value would be the average winnings that were observed by thousands of people playing this machine. The expected value of x, also known as the population mean value of the random variable x, is computed as the summation of x times p of x for all values of x that could occur. Recall example 1, where we had a telemarketing company that called 40 potential customers and recorded the frequencies of the number of magazines purchased by each customer. Let's compute the expected value of the number of magazines purchased on any individual call. In order to do this, we can set up a table. In this table, we should put our x values in the first column, the probabilities of each of these x values occurring in the second column, and in the third column, we should put the heading x times p of x. And in this column, one by one, we should go down the list and multiply each x value times the probability of that x value occurring and record that value in the third column. 0 times 0.4 is 0. 1 times 0.2 is 0.2. 2 times 0.25 is 0.5. We do the same thing with the last two values that could occur. If we sum up this last column, we obtain 1.2, which is the expected value of x. Therefore, on average, the telemarketers can expect to sell 1.2 magazine subscriptions per call. For example 2, how much money should a person expect to win at this casino slot machine? In order to answer this question, we must compute the expected value for this random variable. We do this by setting up the table and putting our x values in the first column, our p of x values in the second column, and we set up the heading x times p of x for the third column. In the first row of this column, we multiply the product of -1 times 5 over 15, which is the probability of -1 occurring, and we get -5 over 15. Then we say 0 times 4 over 15 and get 0. 1 times 3 over 15 is 3 over 15. And we do the same for the last two rows. Summing up all of these values, we obtain 0.33. So the expected value for this random variable is 0.33. Therefore, on average, a person will win 33 cents from this slot machine.
Here we have the formula for computing the variance of a discrete random variable x. And as always, once you have the variance, the standard deviation can easily be obtained by taking the square root of the variance. These formulas can easily be computed by setting up the proper tables. Let's revisit example 1. Recall in example 1, we computed the mean value of the random variable x to be 1.2. In order to compute the variance, let's set up a table with the following columns. The first column should be for all of our x values. In the second column, let's put the probability of each of the x values occurring. In the third column, we should record the difference between each x value and the mean value for the random variable x. In the fourth column, we should square the difference between x and the mean value for the random variable x. In the last column, we should take that squared difference and multiply it times the probability of x occurring. Finally, we should sum up the last column in order to obtain the variance for the random variable x. Once we have the variance for the random variable x, we can obtain the standard deviation by taking the square root of the variance. If we follow that process, we should be able to complete the table as shown on this slide. Notice in this third column, for each value of x, we took the difference between x, which in this case is 0, and the mean value of x. And for this first case, that difference was negative 1.2. We completed this column by taking those differences. In the next column, we squared the difference and recorded the value. 1.44 was equal to negative 1.2 quantity squared. In the last column, we took the squared difference and multiplied it times the probability of that random variable occurring. So 1.44 times 0.4, and we recorded the value here. After summing up the products for this entire column, we discovered that the variance for the random variable x for this problem was equal to 1.46. After summing up the last column, we discovered that the variance for the random variable x is equal to 1.46. The standard deviation is the square root of the variance, which is 1.21. Now let's get some hands-on practice with computing the mean and the standard deviation for a random variable. On this slide, we have the probability distribution for the daily demand of microcomputers at a local store. Now let's get some hands-on practice with computing the mean and the standard deviation for the daily demand for microcomputers. On this slide, we have the probability distribution for the daily demand of microcomputers at a local store. Compute the mean and the daily demand and also compute the standard deviation. You should pause the video at this time and try to compute both of these measures. Now let's check your work. When you computed the mean for the daily demand for microcomputers, your table should look like the table presented on this slide. The expected value is equal to 2.2. When you computed the standard deviation for the daily demand for microcomputers, your table should look like the table here on this slide. Our variance for this data was 1.56 and our standard deviation was 1.25.